Okay, the next question is, what is delta x? So the smallest grid spacing is delta x. The smallest grid spacing has to be small enough to resolve the smallest eddies that are relevant to your turbulent flow field, which are actually Kolmogorov length scale. So should this delta x be exactly Kolmogorov length scale or not? The Kolmogorov length scale is estimated by Kolmogorov's similarity hypothesis, and it is just an order of magnitude, is not an exact number. So important thing is this: your largest wave number, meaning that your smallest length scale, should be high enough to resolve the actual energy dissipation that is occurring in the domain. That is the deriving physical concept. It is not the actual real size or actual wave number of the eddies. Actually, DNS is about resolving the energy, not the scale. So at low wave numbers, we are resolving the turbulent energy generation. Low wave numbers means large eddies. Large eddies are generating turbulence. So they are taking the energy from mean flow and give this energy, uh, generate kind of turbulent kinetic energy for us. At high wave numbers, we are resolving the energy dissipation. We know this. High wave number is the dissipation. So if your number of wave numbers that you put in your simulation, or let's say the smallest delta x that you choose, is enough to resolve the physical energy dissipation that is occurring in the flow, that is what you need for DNS simulation. The delta x is kind of explained in this figure. This is figure 6.16 in Pope's book. And this figure is the dissipation spectrum, meaning that how dissipation is distributed among the wave numbers, how it is distributed among these uh, wave numbers k times eta. The question is, what is the delta x over eta? Delta x over eta, or what is the k max? This is our question. So, as we can see from this figure, the epsilon, the amount of epsilon is very small amount of epsilon. This dissipation, amount of dissipation, this is amount of dissipation. It's very small beyond k times eta equal to 1.5, this point. Very small, you see it. Okay, so your k max should be larger than 1.5. So it's a general criterion for good resolution. Values larger than 1.5 are really irrelevant, and you can just cut off. Let's say use the uh, cutoff criterion for us is 1.5, k times eta equal to 1.5. Larger than that, it's not very important for us. You see, in here you don't have much dissipation. So I will write that delta x over eta, which is pi over k max, it will be equal to pi over 1.5, which is approximately equal to 2.1. So your delta x is approximately equal to 2 times your eta. Eta is dissipation length scale, Kolmogorov length scale. Of course, you can have delta x even smaller than eta. In this situation, your delta x is 2 times eta. You can have, but You can have a smaller than eta, but this will be what we call an overkill. You have seen that DNS, direct numerical simulation, is really computationally resource demanding thing. If you make delta x 10 times smaller than eta, it will be even worse. So in order to prevent that, you have to make a smart estimate of this delta x. And this is two times your Kolmogorov length scale estimation. The motions that are responsible for the bulk of dissipation, they will occur between zero point 0.1 and 0.71 of k times eta, or if you want to represent it as L over eta, it is between 8 and 60. It is considerably larger than the Kolmogorov length scale. Not like we say, okay, uh, uh, this is because of the fact that, let's say, dissipation motions scale with eta, not that they happen exactly at eta. So do not get the wrong message that dissipation exactly occurs at eta. They scale with eta. This is very, very, very important thing. So in summary, in typical homogeneous isotropic turbulence simulation, homogeneous isotropic turbulence, and you want to simulate it, your L over L0 is 8, your delta x over eta is 2.1. So uh, this kind of gives you some estimation of the computational cost of the DNS. There are some few results that can be derived, like, okay, the n cubed is approximately equal to 4.4 times Reynolds number based on your integral length scale to the power of 9 over 4, or a Reynolds number based on your Taylor microscale, which is denoted by lambda in here, and the Reynolds number based on the L is nothing but your turbulent kinetic energy, square root of turbulent kinetic energy times uh, L over nu, and the Reynolds number based on Taylor Mark scale is defined as U prime times lambda over nu. So the important thing uh, in here is the cost of computation. If you just, you see here, you see in the Reynolds number, if you just increase the Reynolds number 2 times, the computational cost will be increased uh, nearly 35 times. You can check it. There is, I will explain it again. I will explain it actually. That's because of very high nonlinearity that exists between this n and the Reynolds number. You see, it is 4.4 times Reynolds to the 9 over 4. So the cost of computation is partly dependent on the n. It also depends on the time discretization that we will talk about in a second. As I said, the Reynolds based on L is a kind of global Reynolds number. Reynolds based on lambda is based on the Taylor microscale. Taylor microscale is some scale that's among the turbulence community is very commonly used. So one thing which is the delta t, Osman asked it. We talked about it, but somehow, of course, whether you are solving using a finite difference scheme or you use a spectral method, you cannot escape from time integration. Time is there. You have to integrate in time. And for that, the time steps have to be very small, as I said. For example, from the results of not DNS, the results of larger dissimulation, LES, of combustors in some studies, uh, we have these results. The combustor is a realistic flow field with much complicated geometry. There is a combustor, there is inlet, outlet, and these things. Uh, uh, the time step was smaller than 10 to the minus 6 in here. And it is LES. It is not, what is it? It's not DNS. So in one example of LES, it was 10 to the minus 6 seconds, the time step. So how do we determine the time step? Actually, the fluid particle has to move only a fraction of grid spacing during delta t. For the determination of delta t, for those of you who might have taken numerical methods or CFT classes, you generally have a very restrict limit, especially for explicit methods called Courant number, right? Courant number restriction. This restriction actually says that this is related to the stability of your integration scheme. It is a very pure numeric thing. So the Courant restriction says that k to the power of 0.5 times delta t over delta x is equal to 1 over 20. And regardless of a numerical method that you are using, there is also a physical based restriction. Physically, your delta t over tau eta tau times eta is equal to 0.1. And you have to remember that when we were trying to find delta x, and I told you not to use 10 times the Kolmogorov scale, you remember, because it will be overkill. That's not a valid argument for time separation. As you see in here, for time separation in this equation, if you that was not very valid argument. For delta x selection, it is the delta x is determined from the physics of dissipation, but for delta t, you have to resolve the actual motion, and these are the restrictions that you can use for your delta t in your simulation. Another question is that, okay, how long should be the duration of the whole simulation? Let's say you have chosen your delta x, you have chosen your delta t, you have chosen your L, but how long you should simulate in physical time? Is it few seconds or it could be a few months? Uh, right now, I'm not talking about the time of computation. The time of computation is already very large. As an example, for one large eddy simulation of this combustor, this is a study in combustor. Uh, the guy has ran it for 1 year. Okay, it was done by Sıtkı Hoca in TOBETU University in Ankara. The code was running for 1 year, and it was simulating only 400 milliseconds. Okay, the code was running 1 year to just simulate 400 milliseconds of flow inside this damn combustor. Okay, these 400 milliseconds could be quite long in this combustor because the total simulation time depends on the time scales relevant to your eddies inside the combustor. For example, the time scale in a combustor flow field, you call it the residence time, meaning that the fluid particle comes into the combustor, okay? The fluid particle comes into the combustor and then leaves it. How long does it stay inside the combustor? It's about 3 to 4 milliseconds. 3 to 4 milliseconds, it's the residence time of one fluid particle. So when you do the simulation for 400 milliseconds, it's quite high for you because you are having 100 residence times inside. So you might not actually want to have 100 residence time. You just need to simulate, I don't know, 5 to 10 residence time of particles. So if the fluid particle stays for 3 milliseconds, I said 3 to 4 milliseconds is enough for you. So it doesn't need to be 400 milliseconds. So for a typical homogeneous isotropic turbulence inside the cube, you're expected to go around 4 times tau. Tau is a very rough estimate of the time scale, and it is turbulent kinetic energy K over your dissipation rate. So if you calculate your tau, 4 times tau will be the duration of the simulation. It's a rough estimate. The number, on the other hand, you can estimate the number of time steps. If it is denoted by m, for those tau second long time, tau second long simulation, the number of time steps will be 9.2 times Reynolds, based on the Taylor uh, scale to the power of 1.5. And when you combine the estimation of n cubed with this m, which is number of m steps, and then your n cubed by m scales with this much number based on both Taylor-based Reynolds and the global-based Reynolds number. So this n3 times m is basically the total number of operations that your computer has to do to finish a simulation, and this simulation takes 4 times tau long seconds. Exactly from this formula, you can estimate that if the Reynolds number is doubled, in this formula, if the Reynolds number is doubled, then the number of operations will be increased by 35 times. I mean, the operations your computer do, or the cost of computation, will be 35 times. And there is a table in Pope's book that gives some examples for you, so I can refer you to this table as well. Okay, by this we finish the DNS. So next week we will start the larger dissimulation.